In this video, we're going to do two examples. They will be derivatives of natural log or exponential functions and maybe both together. So what we have here is y equals the natural log of e to the theta divided by 1 plus e to the theta. So the argument here is very, very complex. One thing that we've talked about is we can use properties of algebra, properties of logs, in order to simplify. So I can rewrite this as natural log of e to the theta minus natural log of 1 plus e to the theta. And I did that using my quotient rule for logarithms. So the log of a quotient would be the log of the numerator minus the log of the denominator. One thing that we notice is the natural log of e cancels, and my function can be rewritten a little bit simpler as just theta minus the natural log of 1 plus e to the theta. So now I'll begin taking my derivative, the derivative of y with respect to theta. Well, the derivative of theta is just going to equal 1. And when I look at taking the derivative of a natural log using the chain rule, it's the derivative of the argument, 1 plus e to the theta, over the argument. So this would be, there's already a minus there. I have d theta of 1 plus e to the theta divided by 1 plus e to the theta. So there I've done my calculus. I have one more small derivative to take. The derivative of 1 would be 0, and the derivative of e to the theta is e to the theta. So dy d theta equals 1 minus e to the theta over 1 plus e to the theta. And that really can't be simplified too much more. This is fine, in my opinion, the way it's. However, we could get common denominators and combine like terms. That would leave me with 1 plus e to the theta minus e to the theta over 1 plus e to the theta. You'll notice that both of these e to the thetas cancel, and this is the same as writing 1 over 1 plus e to the theta. So this is perfectly acceptable as your derivative as well. And it's a little bit more concise than the previous way I wrote it. So we're always looking to simplify things as much as we can. Working through one more derivative, I want to show you can use properties of exponents to help you as well. So here we have y equals e to the cosine t plus the natural log of t. That looks a little funny. Cosine t plus the natural log of t. So we have a big expression in our exponent. Properties of powers say that I must have multiplied two of the same bases in order to add those powers. So this is the same as e to the cosine t times e to the natural log of t. Of course, because those are the same base, this function is y equals e to the cosine t times t. So we've simplified it a little bit. We still have some rules to use. In order to differentiate, I have something times something else. Times or multiply means we would use our product rule. So the derivative of y with respect to t. So the product rule is first times the derivative of the second plus second times the derivative of the first. So here I would have e to the cosine t times the derivative of t, which is 1 times 1, plus t times the derivative of e I'm going to write this one out. E to the cosine of t. So remember, the derivative of e to the x is e to the x. Same with e to the cosine t. However, we would need to use our chain rule and take the derivative of that expression that lives up in the exponent. So I have dy dt equals e to the cosine t plus t. And when I take this derivative, I've got e to the cosine t times the derivative of the exponent, which is times negative sine of t. So the differentiation was very easy there. We just needed to, at this point, we're going to need to clean this up with some algebra. So dy dt equals e to the cosine t, and then that would become minus t sine of t times e to the cosine of t. So you'll notice that both of my terms have an e to the cosine t. I'm going to factor that out. dy dt equals e to the cosine of t, and that would be times 1 minus t times the sine of t. And that would be my final answer. As always, email me if you have any questions.